Good evening, Lamai. Today we are going to study about the standard enthalpy change of formation. The second enthalpy term we are discussing. Right? Okay, first of all, Lamai, let's write the definition here. Let's go to the definition. Then I'll explain right what this enthalpy term means. Right, just go to the definition here. Right, just write at the space given. Right, write it in red color, and afterwards we can box the whole stuff. Right, so just write like this: enthalpy change that occurs in formation of 1 mole of the substance in standard state starting from the reference forms of the constituent elements in their standard states. Right, so that is the definition. Just box this stuff, box that thing. Right, then underline these phrases. Formation of 1 mole of the substance. Just underline formation of 1 mole of the substance. Then underline starting from the reference forms of the constituent elements. Right. So those are the most important parts of this definition. Where the 1 mole stands. So 1 mole stands with the substance to form the delta H naught F, no? Right? Standard enthalpy change of formation, right? So that the 1 mole should stand with the substance to form. This is where the 1 mole stands, no? Right? So 1 mole is with the substance to form. Right? So that is the enthalpy change of formation. That is the most important stuff in any given enthalpy term, where the 1 mole stands. That is clear, no? Then secondly, when studying an enthalpy term, you have to concentrate not only about the 1 mole situation where the 1 mole stands, but also about the things they are at the other side of the equation. So in a chemical equation, you have two sides, no? The reactants and the products. The 1 mole substance will appear with one side of the reaction, maybe as a reactant or as a product. So when studying an enthalpy term, right, you have to concentrate on what appears at the other side as well. The other side than the side appearing with the 1 mole. Right? So in this enthalpy term, the other side of the 1 mole contains the constituent elements at their reference states. Right? Let's discuss what this reference state means. So actually reference state is the most abundant, most seen form at normal conditions. Normal conditions means maybe 1 atm. 1 atm is the normal environmental condition, and the room conditions, right? 25 Celsius or 30 Celsius. The most abundant form, frequently occurring form of an element is referred to as its standard state, right? So if you are referring to the element oxygen, if you are referring to the element oxygen, its standard state, its reference state, reference form. Its reference form is O2 gas. Oxygen appears as a diatomic molecule and with its gaseous state. That is the most abundant form of oxygen. So you know the elemental oxygen is with two forms, O2 gas as well as the O3, the ozone. But most abundant form is the O2 gas. So that is referred to as the oxygen's reference form or the reference state. So when it comes to carbon, the element carbon is with few allotrophic forms, carbon diamond, carbon graphite, even the nanotubes, right? Carbon nanotubes, right? The fullerenes, those are some allotrophic forms of carbon, but the most abundant form at 1 atm and the room temperature is the carbon graphite. The graphite is the most seen form when you are looking at the environment, right? You won't see the diamonds appearing all the way, right? What you see is the stones, black stones, those are graphite, right? So carbon graphite is the carbon solid graphite, solid form, right? Is a reference form of carbon, right? If you think of chlorines, bromine, the fluorine, bromine, iodines, the halogens. So the most abundant form of chlorine is Cl2 gas, appears as a gaseous diatomic molecule. For the bromine, it is Br2 gas. For the not the gas, right? For the bromine, it is Br2 liquid, right? There are only two elements appears as liquids in the room condition. Only two elements in the periodic table appear as liquids in room conditions. What are the two? One is bromine, the other one is mercury. And that is the only metal appears as a liquid in room conditions, the mercury. All the other metals appear as solids, right? So for iodine, it is again coming up with the diatomic form, but as a solid room conditions, it's a solid. So for metals, for normal metals, the sodium, let's say sodium, metallic elements, right? Those will appear as solids in the room condition. So that is a reference form. Those are the reference forms. And for the mercury, it is the only metal appearing as a liquid at room conditions. So the reference form is coming as a liquid. So these are some stuff. For the nitrogen, it is N2 gas, right? So when representing a reference form, you need to come up with the physical state as well. It is very important to write the physical states in physical chemistry. Without physical states, there is no meaning considering the energies of the stuff. So you always know, right? So compared to solids, the more energy is there with the liquids, more kinetic energy is there. Compared to liquids, very high kinetic energy will be there with the gases. So when the physical state changes, their energies will change, right? So energies are related to the physical states. So in physical chemistry, it is very important to come up with the physical states. Without mentioning the physical state, you can't comment on the energies associated with those, right? So that when studying energetics, it's very important to mention the physical state, right? So when it comes to a reference form, you need to mention the physical state as well with the correct form. This is the diatomic form. Some guys are appearing as monoatomic forms, but some are as diatomic forms, right? So phosphorus, if it is P4, right, so kind of polyatomic forms may also appear, right? Okay, these are the reference forms. You got the clear idea. So starting from these reference forms of the constituent elements, you need to construct the right wanted compound. That is what we have are discussing with the standard interchange of formation. Let's come up with some example. Let's come up with an example. Right? Let's come up with an example. Right. So let's come up with some examples which are appearing in your right note. So the first thing, these things are appearing, right? First thing is about standard enthalpy change of formation of H2O liquid. No? Standard enthalpy change of formation of H2O liquid is given as minus 286, no, minus 286 point, so 285.8, no, kilojoules per mole. But this is 285.8 kilojoules of heat will release, 285.8 kilojoules of heat will release when forming, it is all about formation, when forming 1 mole of H2O liquid. When forming 1 mole of H2O liquid. Got the idea? Right. Let's try to come up with the thermochemical equation related to this change. Right? Okay. What is the definition? Again, I am telling you. The definition is it is the enthalpy change occurs when forming 1 mole of the required substance starting from the reference forms of its constituent elements. Starting from the reference forms of its constituent elements, right? Okay. So always when coming up with the enthalpy term, thermochemical equation, first write the substance with the 1 mole. So the 1 mole should appear with H2O liquid in this case. That is the one which is to form the 1 mole substance. 1 mole substance. Right? First write that thing. The most important part. Then the other side of the equation. You have to form this one starting from the reference forms of its constituent elements. What are the constituent elements of this H2O? The hydrogen and the oxygen. What are the reference forms of those? The reference form of hydrogen is H2 gas, the most abundant form of hydrogen in nature. H2 gas. Hydrogen appears as H2 gas. And the oxygen? Oxygen appears as O2 gas. The reference form. You have to start from the reference forms of the constituent elements. The constituent elements are the hydrogen and the oxygen for this compound, and their reference forms are H2 gas and the O2 gas. You have to start from the reference form. Right, those are the most two important stuff with this one. Right? Okay. So after that we have to balance the stuff. The reactants and the products are written. Now we need to balance the stuff. Balance the equation. So when balancing the equation, this 1 mole thing is very important. According to this 1 mole, relative to this 1 mole thing, the equation will be balanced. So this is about the delta H naught F. No? According to this 1 mole thing, respect to this 1 mole thing, the equation is balanced. That means with the 1 mole stuff, always the stoichiometric term is going to be 1. With the 1 mole stuff, always the stoichiometric term is going to be 1. That is how the thermochemical equations are balanced. Relative to that thing, the other components will be balanced. Right? So that you will have two hydrogens at the right hand side. That means there should be two hydrogens at the left hand side as well. There should be two hydrogens at the left hand side as well. So two hydrogens are appearing. That is balanced. As you are with only one oxygen at the right hand side, there should be only one oxygen at the left hand side as well. There should be only one oxygen at the left hand side as well. So that you need to come up with a half here, right? If you have to put some half, that half into 2 is going to be 1, right? One oxygen will have one oxygen is represented from here. So one oxygen it is balanced, right now. Okay, let's come up with the second one. Sorry. Then you can apply this value at the top of the reaction arrow, right? You can apply this delta F value here or at the top of the arrow. So both are okay. So I'll apply the value at the top of the arrow. So it is 285.8 kilojoules mole. So I am again telling you this thermodynamic equation says 285.8 kilojoules of heat is liberated, is releasing when 1 mole of H2O is to form. This is about the formation enthalpy, right? Right. Let's come up with the second example appearing at your note, right? That is about the standard enthalpy change of HCHO gas. Standard enthalpy change of HCHO gas, right? Okay, is standard enthalpy change of formation of HCHO gas is given as -108. Let's try this one. So which is the one to form? It is the HCHO gas, right? HCHO gas, no? Yeah, it's gas, right? So HCHO gas is the one to form. So that is where the 1 mole stands. That is very special in this equation, right? This is the substance to form that should appear with 1 mole. So that equation should appear with 1 mole stoichiometry here. The substance to form. So then we have to start forming the HCHO from the reference forms of its constituent elements. So what are the constituent elements of first of all of this one? The hydrogen, carbon and the oxygen. Those are the constituent elements. Their reference forms are then the hydrogen's reference form is H2 gas, most abundant form of hydrogen, and the carbon's reference form is carbon solid graphite, and the oxygen's reference form is O2 gas. So you have to form this one starting from the reference forms of the constituent elements, right? Now we need to balance this up. Right? So when balancing, the 1 mole thing is very important. You have 2 hydrogens at the right hand side. So 2 is there at the left hand side as well, it is balanced. 1 carbon at the right. So 1 carbon at the left, it is also balanced. So 1 oxygen at the right hand side, so there should be only 1 oxygen at the left hand side as well, so that you need to come up with a half here. So these are the reference forms. Reference forms of the constituent elements. Right now? Let's come up with the third example as well, which is appearing at the next page of your tute. The standard enthalpy change of formation of NH3 gas, right? So that is standard, third one, right? Enthalpy change of formation of NH3 gas is given as -46 kilojoules per mole. That means when forming 1 mole of NH3 gas, 46 kilojoules of heat is released minus exothermic released, right? 46 kilojoules of heat is released. Right, let's come up with this one. So first, the 1 mole substance. This is all about NH3 gas formation, right? That is where the 1 mole stands. That is where the 1 mole stands. So we have to start from what? We have to start producing the NH3 from reference forms of its constituent elements. The NH3's constituent elements are nitrogen and hydrogen. Nitrogen and hydrogen. So nitrogen appears as a diatomic gas at the normal conditions. So that is reference form. And hydrogen will appear as again as a diatomic gas at the normal conditions, room conditions. So that is the reference form. So the reference forms are written. Right? Then balancing. When balancing, always the equation should be balanced relative to the 1 mole substance. This is the enthalpy of formation of NH3 gas. So 1 mole appears with the NH3 gas. To relate to this thing, the whole equation will be balanced. So you should have only 1 nitrogen at the whole equation. So at the right hand side, just 1 nitrogen is there. So at the left hand side as well, you should have only 1 nitrogen. For that, you need to come up with a half here. Half into 2 will give you 1. When it comes to hydrogens, 3 hydrogens are appearing at the right hand side. So that 3 hydrogens should be there at the left hand side as well. So how to come up with 3 hydrogens with this one? First of all, just divide by 2, to cancel off this 2, just divide by 2, then multiply by the needed number. You need 3 hydrogens, no? So multiply by 3, as you have cancelled off the 2 by dividing. So this will represent 3 hydrogens at the right hand, at the left hand side. So you can write the change at the top of the reaction arrow, minus 46 kilojoules per mole. Here as well, you can write the enthalpy change at the top of the arrow, kilojoules per mole. Right now? So this is how the equations are to be written, the thermochemical equations are to be written. So now I normally even write in the chemical reactions as well as thermochemical reactions, this one thing is not written, right? 1 as the stoichiometry is not written. හරි. stoichiometry එක 1 කියලා ලියන්නේ නැහැ නේ ළමයි. හරි. ඒක ලියන්න එපා ඉතින්. හරි. මම මේක ඔයාලට ඉගෙනුවේ with relative to the 1 mole you have to balance the stuff, right? Don't write that one, right? ඒක ලියන්න එපා. හරි. ඒක ඔළුවේ තියාගෙන balance කරන්න. Right නේද? හරි. So just copy this stuff and then you have some exercises. Some exercise at the page number 16. You can do that as well. First copy the stuff. Right නේ? හරි. එහෙනම් අපි බලමුද ඔයගොල්ලගේ exercises වල answers ටික. Right? So at the page number 16 you have some exercises. Let's discuss the answers for the question number 4 to 10. Those 7 enthalpy terms. Right. Right, first I'll write the stuff appearing in your tute, right? So number 4, it is delta H. It is about writing the thermochemical equation for delta H not F, CH3COOH liquid. Right. Number 5, is about delta H naught F CH3OH gas. No? Number 6 is about delta H naught F NaCl solid. Right. Number 7 delta H naught F AgI solid. Number 8 delta H naught F Na2O solid. Number 9 delta H naught F sodium carbonate. Right. So number 10. So we'll write the number 10 after completing this stuff, right? So let's do the stuff. Right. First one is about the formation enthalpy, standard enthalpy change of formation for CH3COH liquid. Standard enthalpy change of formation for CH3COH liquid. So one more stands with the forming substance with the CH3COOH liquid, right? So let's start with that, right? That is the place to start, right? Right. Starting with CH3COOH liquid. It appears with 1 mole situation, right? 1 mole. This is where the 1 mole appears, right? Okay. You have to start from the constituent elements. Its constituent elements. What are the constituent elements? The carbon, hydrogen and oxygen. Those are the constituent elements. Their reference forms should be written here. For the carbon, its reference form is carbon solid graphite. For the hydrogen, reference form is H2 gas. For the oxygen, reference form is O2 gas. Starting from those you need to produce CH3COH. Here, right? Right now. Okay. So this is all about the delta H naught F formation of CH3COH liquid, right? Right. Now we need to balance this stuff. So you have 2 carbons. So you need to come up with 2 here. So balancing will be done. Right, respective to the 1 mole stuff, right? This is the 1 mole stuff, right? This is where the 1 mole stoichiometry appearing. So 2 carbons are there at the right hand side. So at the left hand side as well, you should have 2 carbons, right? Then you are with 4 hydrogens here at the 1 mole stuff. So you need to come up with 2 here for the 4 hydrogens, and you are with 2 oxygens. So 2 oxygens are appearing. So that is the equation. This is the thermodynamical equation, right? So this one. First of all, just write the 1 mole stuff. This is about delta H naught F, the 1 mole stuff. So 1 mole species is CH3COH. Sorry, CH3OH. CH3OH is the 1 mole species here. Gas. Because it should be written right correctly. Then this side. Right? So you have to start from the reference forms of the constituent elements. What are reference forms? You have the carbon, so it is the carbon solid graphite. So you have hydrogens, so hydrogen's reference form is H2 gas, and you have oxygens. Oxygen's reference form is O2 gas. Starting from them, you need to form the CH3OH gas, right? So now we need to balance this stuff. This is where the 1 more thing appears with the substance to form, as we are discussing about the standard enthalpy change of formation, right? So 1 carbon is appearing, so 1 carbon is balanced. 4 hydrogens are appearing, so you need to come with 2 here. 1 oxygen, that means should have some half here. Right now, this one. The standard enthalpy change of formation of NaCl solid. So this is about formation enthalpy of NaCl solid. So what are the reference forms of these two constituent elements? Sodium appears as a solid. All the metals will appear as monoatomic solids other than the mercury. Other than the mercury, all the metals will appear as monoatomic solids, right? Only mercury will appear as a liquid. Other than mercury, all the metals will appear as monoatomic solids. And those are the reference forms, right? And for the chlorine, the reference form is Cl2 gas. You have to start from the reference forms of the constituent elements. You have one sodium is one sodium, but just one chlorine, so that you need to come up with the halves here, because we need to, right, have number 1 here, right? This number 1 can't be changed with the substance to form. That is where the 1 more stands. According to that, relative to that, the other species should be balanced, right? No? Okay. Here, standard will be change of formation of AgI solid. So substance to form is AgI solid. So you have to start from the reference forms of the constituent elements. The constituent elements are silver and iodine. The reference forms are silver solid and I2 solid. Iodine appears as a diatomic solid in room conditions, right? That is going to be the reference form then, right? So one silver is there. This is where the 1 more stands. One silver is there, so there is 1. It is balanced. One iodine is there, so you need to come up with a half here, right? So that is how the things are to be balanced for the correct thermochemical reaction. So appearance of these half values as stoichiometric values is okay when it comes to, right, thermochemical reactions. Right? Thermochemical reactions කතර පස්ලා ළමයි මේ half values equation එක apply කරන එක අවුලක් නැහැ. Right? No worries. But for normal chemical reactions you can't do so, right? Always you need to come up with the simplest integer ratios, right? The smallest integer ratios, small ratios, but the smallest values and the integer values should be there with the chemical reactions. But for thermochemical reaction balancing, you can use fractions, no worries, because we are mainly concentrating on the species which stands with the 1 mole. Relative to that, the balancing will be done. That is why the half values are allowed, right? So for this one, so this is about the standard enthalpy change of formation of sodium oxide solid, Na2O solid, right? Let's balance this stuff. Na2O solid, right? So the constituent elements, the sodium and the oxygen. The reference form of sodium is sodium solid. Oxygen's reference form is O2 gas. So you are with 2 sodium atoms, so you need to come with 2 here and just 1 oxygen here, so that this should be multiplied by half. So that is the formation enthalpy of sodium oxide solid. For this one, there is the enthalpy change of formation for sodium carbonate solid. Sodium carbonate solid. So it is going to be the sodium solid as reference forms, right? Sodium solid. And for the carbon, the reference form is carbon solid graphite. Carbon solid graphite form. And as a reference form for the oxygen, it is O2 gaseous form, O2 gas. O2 gas is a reference form of oxygen. Let's put the numbers. You need to have 2 sodiums, right, with the 2 sides, right? So this is where the 1 more stands, right? So 2 sodiums are appearing at the right hand side, so that 2 sodiums should be there at the left hand side as well. So 1 carbon is 1 carbon and 3 oxygens should appear. How to come up with 3 oxygens here? First divide this thing by 2, then this 2 will be cancelled off. So as you need 3 oxygens, so just multiply by 3, right? So that is the standard enthalpy change of formation of Na2CO3 solid, the thermochemical equation, right? So let's come up with the 10th one as well, number 10, that is for the KNO3 solid. Number 10 is with the for the delta H naught F of KNO3 potassium nitrate solid, right? Let's write the thermochemical equation of this thing. So first the one more stuff is all about delta H naught F of formation of potassium nitrate solid. So that is where the one more stands. So then the reference forms, right? So reference form of fossil potassium, it's a metal, so coming up as a solid, right? Then the reference form of nitrogen, right? It is the N2 gas, right? And the reference form of oxygen is the O2 gas, right? Now we need to balance the stuff, right? One potassium appearing, okay. One nitrogen appearing, so that you need to come up with a half here, right? And 3 oxygens are appearing. 3 oxygens are appearing. That means first you need to divide this by 2 to come up with 1 oxygen. Then you need such 3 oxygens, right? So that you can apply 3 here. So in this manner, you can balance the thermochemical equation for the standard enthalpy change of formation of KNO3 solid, right now. Okay, so things are done, right? That is all about the exercise there, the question number 4 to 10, right now, the stuff are given, right? Just do your corrections if needed. Right, okay, this is clear, right? Let's discuss about some new stuff. Actually, it is not appearing in it is appearing in your note, right? Let's discuss about the second point appears at your page number 15. We haven't discussed that thing, even though I have introduced you the reference forms, what they are. Still, I haven't discussed about the enthalpy changes of formation for the reference forms, right? Strange change, okay, strange. Let's discuss about that. Enthalpy change of formation of reference forms. Let's discuss what will happen. That is there in your second point at the page number 15. Anyway, let's discuss the idea there. I am now going to discuss about the enthalpy change of formation of reference forms. See what that means, right? This is important, no? When solving questions, knowledge of this thing is important. See what I am going to discuss now. It is the enthalpy change of formation of reference forms. Reference forms of elements. Right? See what this means, right? Reference form of elements. The idea is this now. Let's take this as an example. Let's take this one. The delta H naught F of O2 gas. So we know O2 gas is a reference form. That is a reference form of oxygen, right? O2 gas is the reference form of oxygen. Oxygen. See how this looks like. What is this value? So we can write this thermochemical equation here for the enthalpy change of formation for the O2 gas. So you have to produce O2 gas, 1 mole of O2 gas, starting from reference forms of the constituent elements. What are the constituent elements? Actually, what is the constituent element of O2 gas? It is the oxygen, right? So you need to start from the reference form of that thing. So the reference form of oxygen is oxygen gas, O2 gas. So you clearly see, right? This is balanced, right? And you clearly see the two things at both sides are the same. Actually, no change at all going from starting state to the final state. This starting state, this is the final state, initial and the final. Going from initial to final, no change at all happened. So that there is no involvement in energy here. No involvement in energy change. As no change at all happened, no change happened at all. No energy change is needed to convert this state to this state. So actually, this value is 0. No releasement of energy, no absorbment of energy to convert this state to this state, because both are the same state, right? So enthalpy change of formation of O2 gas, the reference form, is equal to what? 0. Let's come up with another one, another example. Let's think of the enthalpy change of formation of carbon solid graphite, which is the reference form of carbon. See, let I like here, right? See how it looks like. So you have to produce the carbon solid graphite. This is where the one more stands. This is where the one more stands. Starting from the constituent elements of this thing, that is carbon, at its reference states. The carbon's reference state is carbon solid graphite. So you clearly see no change happened going from here to here, going from initial to final. No change happened at all, right? So no change means no energy involvement when converting this to this. Actually, no, it is not converted. Actually, the same state appearing at the initial point as well as at the final point. With time, no change occurred to the system. Same state appearing as the initial at the final state. Right, so no change at all, so energy involvement is 0. No heat released, no heat absorbed. So this value is equal to 0. So what is the conclusion we can make from here? So you can say the enthalpy change of formation of a reference form is equal to 0, is equal to 0. So one can say delta H naught F of a reference form is equal to 0, is equal to 0. This is the final conclusion we can make from this stuff, from the things we have learned now. Right now, reference form. It should be okay with the physical state as well. Right? The idea is clear. So that is what it is given at the point number 2 of a page number 15. See, it says, because the formation of the most stable form of an element from itself, formation of the most stable form of an element from itself is no change at all. The standard enthalpy change of formation of pure element at its reference form is 0. Pure element at its reference form is 0. Right now, the idea is clear. Right. Okay. So let's go towards the next point we need to learn, which is appearing in the page number 16. Right. Is that clear now? Right. The next thing. So we have studied about the delta H naught R last day, the enthalpy change of reaction last day, and today we have studied, up to now we have studied about the delta H naught F, the enthalpy change of formation. Right. Now I am going to relate these two stuff. There is an equation relating these two guys, these two enthalpy terms, the delta H naught R and the delta H naught F. So what is the equation? It is this equation. So we can find out the enthalpy change of reaction for any given reaction if we know the enthalpy changes of formation, if we know the enthalpy change of formation of all the reactants and products, if you know the enthalpy change of formations of all the products as well as the enthalpy change of formations of all the reactants if we know those, actually we can use this equation where you take the summation of all the enthalpy change of formation of products and the reactants, you get the summation of those things and you have to subtract them. Right. So this reaction will give you the delta H naught R of any given reaction. Right. What you need to do is, first you need to know the delta H naught F values of all the reactants and the products, all the components of the reaction, right? Then you have to take the summation of delta H naught F values of products and you have to subtract from that thing, you have to subtract this value, right? The delta H naught F values of reactants. So with the use of this equation, you can come up with delta H naught R of any given reaction, right? The most important stuff to know here, to use this equation to find out delta H naught R, right? You should know delta H naught F, the formation values of all the components, all the reactants and products appearing at the equation, appearing at the reaction. With this knowledge, you can come up with a delta H naught R. So I'll prove this one, right? Up to this time, don't think of how this came, right? Don't think of that. I'll prove this thing later at the same lesson. Today I'll prove this later as the final section of the today's lesson, right? Just take this one as it is for this moment, right? So let's use this one to come up with the delta H naught R with some example. So such an example is given with the page number 16. So problem solving using this equation, right? So there are my little correction is there, just do the correction. It is said like problem solving using delta H naught R, it should be delta H naught R equals to, right, that bold stuff, right? Problem solving using delta H naught R equals delta H naught products minus delta H naught reactants minus delta H naught reactants. This sigma term is not needed, right, to written, right? If you written the sigma term, that is perfectly correct, but without writing the sigma term also you can represent the relationship. No worries, you won't lose marks if the sigma term is not appeared with the answer, right? No worries, but with the sigma term, that is the perfect answer, right? Anyway, right, so it should be corrected as delta H naught F of reactants. There's a printing mistake appearing as a reaction. No, it is not the reaction, delta H naught F of reactants, right? Same problem is appearing with the answer as well. When seeing the answer also, it should be corrected as reactants, right? Okay, let's write it here. Right, let's apply this one. So this is the equation we are studying. It's kind of example, right? So we have to study this equation C6H6 liquid, no, plus 15. Let's go through the reaction appearing in node. 15 over 2 O2 gas giving you 6 of CO2 gas plus 3 of H2O liquid, right? So let's you are supposed to come up with the delta H naught R here for this reaction, right? Okay, and some data are also given, right? Some data are also given. What are the data given, right? Some data are also given. The compound and some of delta H naught F values are given in kilojoules mole, right? So C6H6 liquid, CO2 gas and H2O liquid. These data are given minus 84 kilojoules mole, right? Minus 393. These things are appearing in your note, right? 286. Right. Let's use this data, right, to come up with the delta H naught R of this reaction. So it will be done like this. So first write the equation. So we can write the equation like relationship like delta H naught R is equal to delta H naught F of products minus H naught F of reactants. Normal lamai, when taking a change, it is always the final minus initial, no? Final minus initial, no? So in a reaction, the final state is the product state and the initial state is the reactant state. So it is all about final minus initial. So products minus reactants, right? So now let's apply the values here for the equation. Substitutions. Basically, it should be done with the correct weights. The substitution should be done with the correct weights. Those are 3 marking points in a, right, this kind of answer, no, in chemistry, coming up with the correct equation, right? Substitution with the correct weights, then final answer with the correct weights, right? Let's do those 3 steps with this one. So delta H naught values of products. So what are the products? CO2 and H2O, right? To produce to form 1 mole of CO2, to produce 1 mole of CO2, 393 kilojoules of heat change should be done. To produce 1 mole of, it's about 1 mole, no? Formation, to produce 1 mole of CO2, minus 393 heat change should be done. But here you have 6 moles of CO2s. That means CO2, 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 like this 6 times the CO2 is appearing. So that 6 times of the formation of CO2 should be provided to do that change. Should be written as the delta F for the product side, right? So CO2's value is minus 393. Minus 393. This is the delta F values of CO2, guys. 6 of CO2, guys. The summation. Plus, what about the H2O? To form 1 mole of H2O, you need minus 286 kilojoules of heat change. But such 3 H2Os are appearing. So, it should be multiplied by 3. Right? This is all about the summation of delta F values of products. Then minus the reactants, the values of reactants. So you have C6H6, just 1 mole to produce, just 1 mole to form. So that carries minus 84 kilojoules of heat change, right? Plus this thing, it is not provided, but you should know the value. What is the delta H value of O2 gas? As it is the reference form, it is a reference form of the oxygen, elemental oxygen. It's a reference form of the oxygen, element oxygen, the O2 gas. So for a reference form, the delta F value is going to be 0. So 15 into 2 into 0. 15 into 2 into 0 is just 0, right? Any number multiplying with 0 is 0. So this is the substitution with the correct units. Units should be written. All the values are represented in kilojoules per mole. Substitution with correct units. So you can come up with the answer by simplifying this stuff, right? So the answer would appear as 3000, right? 132. The minus. Just do the simplification, right? And you can come up with the answer. So that is how you're supposed to use the equation to solve for delta R, right? Just complete the stuff. Actually, that thing is appearing in your note. Just go to the note and see whether you understood the whole concept. Here, some change should be done with this one, right? Here it is written as delta F of reaction. It should be reactants, right? Do that change with your note. Right now. So just do the questions appearing in the page number 17 and 18. You have 2 questions to solve using this equation. Just do those 2 stuff, right? Right. Let's discuss the question appearing at page number 17. See. This is the question number 1, right? So let's solve the 1 and 2 there. Right? You have 3 of magnesium solid plus Fe2O3. Right? Lama, it should be solid, right? It's not written, it should be solid, right? Always some physical state should be written. So this is the reaction, right? 3 of magnesium oxide and 2 of Fe solid, no? Right. So delta R is the one to calculate here. Right? Okay. Let's do this one. And some values are also given. Species and delta H naught F values are given for the Fe2O3 solid as well as for the magnesium oxide solid. The values are given. This is minus 825. This is minus 616. Let's solve for this one. So we can write the relationship first of all. That is delta H naught R is equal to delta H naught F of products minus delta H naught F of reactants. Right? So let's do the substitutions, right? So as products, magnesium oxide and Fe solid are appearing. So you are with 3 of magnesium oxides to form, as the ratio F of 1 of magnesium oxide is 616, to form 1 mole of magnesium oxide, it is this enthalpy change should be done 616, but we have such 3 magnesium oxides, so it should be multiplied by 3. And the ferrous solid appearing, so this is going to be the reference form. This is a reference form, right? This is a reference form of this metal, so that its delta F value is 0. Delta F value is 0. Right now, this is all the reactants. Then minus the products. Sorry, this is about the products. Now minus the reactants. So you are with 3 magnesium, guys, but the magnesium is kind of reference form. Right? Metal solids, monoatomic metal solids are reference forms, right? So the 0, 3 into 0 is 0, plus you have 1 Fe2O3 appearing here. So to form 1 mole of Fe2O3, this heat change should be done, minus 825. Right? So substitution with correct units, you should be mentioned, kilojoules per mole. So you can simplify this stuff. Let's do the simplification, right? So it is like 3 into 660, that value minus becomes plus, no? 825. Right? No? So this is minus, sorry, this value is minus, right? 616 is minus, right? Sorry for that. So this is a minus value and this is a plus value, right? Minus plus, no? This is given as minus 1023 kilojoules more. You should get this answer, right? Right? That is about the first question. Let's do the second stuff as well. So which is appearing at the next page, the second one. So first I'll write the question here, right? So you have to do some correction, Lama, there. It should be C2H6, right? It should be C2H6 gas reacting with 7O2O2 gas, right, to produce 2 of CO2 plus 3 of H2O liquid. So this is about delta H naught R, right? Okay, and some data are given for some compounds, right? For the C2H6 gas, CO2 gas, and for the H2O liquid, the different F values are given as minus 84, minus 394, minus 393, sorry, and as minus 285 right? So we are supposed to come up with the delta H naught R for this reaction, right? Let's do the stuff, right? First, coming up with the correct equation. So it is going to be relation R is equal to the summation of enthalpy change of formation of products. Final one is initial, right? Products minus summation of enthalpy changes of reactants, right now? Okay, let's do the substitution, right? So as products, you have CO2 and H2O. 2 of CO2s are appearing, so 2 into CO2's formation, so that is minus 393 plus 3 into H2O's formation. The H2O value coming up as minus 285, right? This is the change of formation of products, the summation, right, minus the change of formations of reactants, right? As reactants, C2H6 and O2 are appearing. C2H6, its value is 84, just 1 is there, so you can apply directly the minus 84 there. And the oxygen, it's a reference form. It's a reference form. Reference form of oxygen is the O2 gas. So its formation value is going to be 0. No need to give that value, they won't give you the value, right? So you should know that point there. That is your knowledge, right? Then the change of formation of a reference form is equal to 0. That is your knowledge. So substitution should be done with the correct units, so you need to apply the unit as well. Okay, so simplify this thing to come up with the answer. So it is going to be like, all right, 393 into 2 is there, 93 into 2 is there, right? That is 786 minus, and you have 285 into 3 minus 5. No? 285 into 3, right, into 3, that is given as minus 1641. This becomes plus, minus minus plus 84. This is 1557, no? 1557, right? Positive. Answer with the correct units, right now? Okay, just complete the stuff now. This is clear, right? So let's move to the next section, right? Things are clear. Let's move to the next section, right? So now we are going to discuss about construction of thermochemical cycles. Construction of thermochemical cycles. That is the next topic to study here. Thermochemical cycles. Thermochemical cycles, right? Thermochemical cycles, right? See, how to construct these things, thermochemical cycles, right? Okay. Thermochemical cycles. Right. So actually, there are few methods. There are few methods to solve these calculations, solve these problems in thermochemistry. Basically, there are four methods. There are four methods in problem solving. Four techniques we use in problem solving in thermochemistry. One method is discussed using equations. Right? That is one form of doing problem solving in thermochemistry. The second and the most frequently used technique is this one, using a thermochemical cycle. Sometimes this is referred to as the Hayes cycle, thermochemical cycle or the Hayes cycle. Using that a diagram referred to as thermochemical cycle or the Hayes cycle, we can solve this problem appearing in the thermochemistry. That is the second form. We have some two forms as well, using AG diagrams as well, so enthalpy diagrams as well as the algebraic form. Those are the other two forms. Anyway, now we are going to study about constructing a thermochemical cycle and how to use a thermochemical cycle to solve these problems appearing in the thermochemistry. Right? Okay. So I'll do the right. The first question. I'll solve the first question. Right, which we have done using the equation, but now with the use of a thermochemical cycle. Right? Thermochemical cycle like use කරලා මම දැන් ඔයාලා කලින් solve කරපු equation එක solve කරපු question එකම නැති problem එකම solve කරන්න තමයි යන්නේ. Right? With this we'll gather some knowledge about constructing a thermochemical cycle. Right? So it's right, solving the same problem appeared at page, what was the page? It's page number 17, right? Problem number 1. Solving the same problem number 1 appeared at page number 17 using a thermochemical cycle. Right? Let's do the stuff. Right? First of all, what was the question? When using a thermochemical cycle, right, to solve problems, the first thing to do is first write the thermochemical equation, so thermochemical reaction relevant to what they are asking, means relevant to the goal. First write the thermochemical equation relevant to the goal. Goal means relevant to the problem, relevant to the question that they are asking. In this case, they are asking us to find out the delta H naught R of a given reaction. Right? So first thing to do is write that given reaction which we need to solve for delta H naught R. Right? So that reaction is what? That is the reaction is given as 3 of magnesium solid. The reaction appeared at page number 17. The first question, solid plus Fe2O3 solid. Even they are asking the delta R of this thing, and 3 of magnesium oxide solid as well as 2 of Fe solid would appear here. So we are supposed to solve for this thing. So first write the thermochemical reaction relevant to the problem they are asking, to the question they are asking. That is the first step in constructing a thermochemical cycle, right? Okay. Then let's come across the data given in that thing, right? So we need to study that thing. So species and delta H naught if values are given for the Fe2O3 as well as for the magnesium oxide, right? The values are actually minus 825 and the other, for the other it is minus 616. No, these values are given, right? This data given. Right, the first step is done. Now the second step to follow in constructing a thermochemical cycle. The second step to follow is like this lemma. So basically, cycle means, for a cycle, right, should have at least 3 stages. For a cycle, at least 3 stages should be there. This is not a cycle now. Cycle like so අඩුම ගාන ඉතින් ස්ටේජස් 3ක්වත් තියෙන්න ඕන සයිකල් එකක් මොකක් හරි කරගන්න. ඉතින් ඒක තරණයල්ලම නේද? අර පොඩි කාලේ ඉඳන් නේ මදුරුවාගේ ජීවන චක්‍රය. හරි. චක්‍රය නේ සයිකල් එක. හරි. එතකොට ඉතින් රවුමක් තියෙන්න සමනලයාගේ ජීවන චක්‍රය. හරි. ඒක අඩු ගාන සයිකල් එකක් වෙන්න ළමයි නේද? අඩු ගාන ස්ටේජස් 3ක්වත් තියෙන්න ඕන. නැත්නම් තීරුමක් නැහැ. හරි. ඒක වැඩක් නැහැ. හිම සයිකල් කෙනා දෙකක් තියෙනවා. At least 3 stages. Right? At least 3 states should appear for a cycle to be constructed, right? Okay, hari niyan. තුනක්වත් තියෙන්න ඕන, right? ඒක නිසා so now we are supposed to construct at least one imaginary state to construct a cycle out of these things. cycle එකක් construct කරලා අඩු ගානේ states තුනක්වත් තියෙන්න ඕනේ. ඉතින් තුන්වෙනි set එකත් අඳ ගන්න වෙනවා. So I am trying to construct a new state, some imaginary state, right? I am trying to construct some imaginary state here. Third state or imaginary state. At least one imaginary state should be there. At least 3 states should be there to complete a cycle, right? Even if 4 states in at least 3. And the other thing you should know is actually as a thermochemical cycle, right, we are discussing about the same system, right? Right, when drawing a thermochemical cycle, we are discussing about the same system, even though different states are appearing with that same system. So in a thermochemical cycle, we are discussing about the different states of a same system, right, Laman? Different states of a same closed system is discussed with the thermochemical cycle. Sorry, එකම closed system එකේ different states තමයි අපි thermochemical cycle එකෙන් කතා කරන්නේ. එකම closed system එකේ. That means all the 3 states. So now we have 3 states with the imaginary state. You have 3 states. The first state, initial state. So one gets any. This one and this one. So 3 states are there. of the same system, same closed system. Remember, the same closed system, right? As a thermodynamic cycle, right? We construct, right? Thermodynamic cycle means a cycle containing different states of a same closed system. Different states of a same closed system is considered as a thermodynamic cycle, right? That means the mass should be conserved with each and every state of your thermodynamic cycle. Even in the immediate state, the mass should be conserved. That means the atoms at one state, the number of atoms at one state should be there at all the states. Number of magnesium atoms at this state should be there at all the states. Here also 3 magnesium atoms should be there, here also. Number of Fe atoms at this state should be there at the other 2 states as well. For the oxygen also the same. So mass should be conserved, keep that in mind. If not, if you had a constructor drawn without the mass conservation, the whole cycle is wrong. You won't get marks, 0. Right? Okay, let's try to complete the cycle. So our next problem is actually what we are supposed to write it here. What we are supposed to write here at the imaging state. So if we are able to come up with the imaging state, then we can relate that imaging state to the other 2 states with the use of arrows and the energies. Right. First of all, we need to come up with this state, the components of this imaging state, the chemical components. How to come up with this thing? So to decide the components of the this imaging state which we are going to build, right? First look at the data given. First look at the data given. What are the data given? Yes, the data given are all about formation enthalpies here. Data given are all about formation enthalpies here. Formation enthalpies here. Right? And then think of what kind of species appearing with the data given. With the formations, what kind of species appearing? The 1 mole compounds, and the reference forms of the constituent elements. 1 mole compounds and the reference forms of the constituent elements appears with formation enthalpies. Right? Examine the data given. Then see the missing pieces of your diagram, missing pieces of your cycle, of your diagram. So already the compounds are written. Right? But not all the reference forms of this system is written so far. This system means, this closed system means it's a system containing 3 magnesium atoms, 2 Fe atoms, and 3 oxygen atoms, right? It's all about this system. The thermodynamic cycle is all about this system. The compounds are written, 1 mole compounds are written, but the reference forms of all the elements of the system is not written. Some of the things are written, but for the oxygen it is not written. So that is the missing piece. That is what we have not written so far in our diagram. So it is better to come up with the reference forms, of the constituent elements of the system as the imaginary state, as the immediate state, right? So that it is also available in your diagram. Let's do the stuff. So we are going to construct this immediate state with the reference forms. So with this system you have 3 magnesium atoms. So magnesium's reference form is magnesium solid. You have 3 of those. And with this system you have with 2 Fe atoms. So Fe's reference form is Fe solid. And with this system you have 3 oxygen atoms. So oxygen's reference form is O2 gas. So you need to have only 3 oxygen atoms, so that cancel everything in the 2 and 3. So 3 oxygen atoms. This is going to be your immediate state. Constructing this is very important, right? So the immediate state is done. The second step is done. First thing is write in the expected thermochemical reaction. If they are expecting you to come up with the answer. Then second step is coming up with the immediate state or immediate states. Third thing, when constructing a thermochemical cycle, third thing, it is the, right, it is all about the energy changes you need to do to convert these states to immediate state or immediate state to these states. The third stage is all about relating these 3 states, means relating the immediate state to the other 2 states already. So you should have come up with some reaction arrows like this, like this, or this, or you have to relate this thing from a reaction arrow like this, or this kind of arrow, right? You have to relate this immediate state. You have to combine. You have to match this rate with the use of energy changes, right? Okay. So let's do the stuff. Right? You can convert this imaginary state to this state. You can convert this imaginary state to this state. You can convert this state to this state by just converting these 2 guys to Fe2O3. Because with both the states we are referring to now are with same 3 magnesium solid atoms. Same 3 magnesium solid atoms. So no change happened with the magnesium solid when converting this to this. What has happened is actually the 2 of Fe solid and 3/2 of O2 gas has been converted to Fe2O3 solid here. That is the change occurred when converting this imaginary state to this state. So actually that is all about the formation of 1 mole of Fe2O3 solid. This is all about the formation of 1 mole of Fe2O3 solid, right? Right now, this is the change we are doing now. This is all about the formation of 1 mole of Fe2O3 solid, right? So that will carry this amount of energy change. Formation of 1 mole of Fe2O3 solid carry this amount of energy change. So that is minus 825 kilojoules per mole. Right now? So by applying this energy change, you can convert this immediate state to this state. No change with the 3 of magnesium solid, and these 2 are changed to this one when applying this formation enthalpy of Fe2O3. Right now, the things are clear. That is how we are supposed to convert this to here. That is done. Right? Okay. Let's try to connect these 2 states as well with energies. Right? Okay. Now I'm supposed to connect those 2 states, right? Next one. So no need of write in these boxes, right? I have written the boxes to give you the clear idea, to concentrate on that part only. Next thing, now we are going to relate this state to this one. We're going to relate this state to this thing, right? First, see what kind of a change has happened when converting this to this. What kind of a change has happened when converting this to this, right? So for that, first look for the unchanged species. So 2 of Fe is appearing here as well as here. 2 of Fe solid is appearing here as well as here. So no change with the 2 of Fe solid there. So that the only change occurred is actually converting this 3 of magnesium solid and 2 of O2 gas to this one. So this is the change occurred. 3 of magnesium solid and 3/2 of O2 gas has been converted to 3 of magnesium oxide. That is the change actually happened when converting our image state to this state. Nothing happened with the 2 of Fe. So actually then look at only of that change occurred here. Actually this thing is converting 3 of magnesium with 3/2 O2 to this one is actually 3 times of the magnesium oxide's formation enthalpy. So converting the reference forms of the constituent elements to the compound to 1 mole of the compound is referred to as the formation enthalpy. But here now we are supposed to produce 3 moles of the compound. To form 1 mole of the magnesium oxide starting from the reference forms, you need 616 kilojoules per mole. But now we need to produce 3 moles of magnesium oxide starting from its reference forms. So to produce 3 moles of magnesium oxide, you need to apply 3 times of the energy change needed for the 1 mole, right? So 3 times of the energy change needed for the 1 mole will give you the energy change for 3 moles of magnesium oxide, right now? So if you are to apply this energy change on this image state, that image state will convert to this one. Basically, these two guys at this image state will convert to this one. That means this state will completely convert to this state, because 2 of unchanged Fe2 is appearing with both states. The thing is clear now? This is how we are supposed to complete your thermodynamic cycle. The cycle is completed. Now you can clearly see a cycle. All the states are right connected with reaction arrows, connected with energy changes. So the cycle is completed, right? Okay. So we have 3 states and the cycle is completed, right? Constructing the thermodynamic cycle is done. Now the next thing is using this constructed thermodynamic cycle to come up with the answer for the delta H R. To come up with the answer for the delta H R, now we are supposed to use this cycle. How to use this thing to come up with delta H R? Right, let's discuss. So to use this to come up with delta H R, first of all we need to identify the initial and final state of this system. Now we have a system. Now we have 3 different states of one same system. Now we have 3 different states of one same system, right? So now we need to come up with the initial and final states of this system to solve for delta H R, to apply the rules. So what is the initial state and what is the final state of this system? The initial state is the state where all the arrows begin. So what is that? all the arrows are starting from this state, right? All the arrows are starting from this state. So this is your initial state. This is your initial state. This is your initial state. Right now? Then what is the final state? What is the final state? Final state is the state where all the arrows ints, right? So this is going to be your final state. All the arrows coming towards that state, right? So all the arrows int here. So this is the final state. The final state, right? Okay, so we can now apply the rule. We can apply some rules for state functions to solve for delta H naught R. We know for state functions, we have learned that, right? When the initial and final states are same, the magnitude of change of a state function only depends on the initial and final state. When the initial and final states are same, right? Even though you did that change from this route or from this route, there are two routes available now to come to the final state starting from the initial state. Two routes are available. We can go from here to here directly from this route, or we can go from here to here, initial to final, from this route as well, going to here and then here, right? So as this one is a state function, the enthalpy, we can say the magnitude of change going from here to here by this route will be equal to the magnitude of change going from here to here from this route. You can use any path tree as long as the initial and final states are same. The enthalpy change is the same. The change in the thermodynamic property is the same, right? So let's apply that rule that says the enthalpy change happened when going from this route to the final state starting from the initial state is this plus this plus this. That will be equal to the enthalpy change occurs when going from this route, that is this value. So this plus this is equal to this. So we can write minus 825 kilojoules per mole plus delta H naught R is equal to this plus this is equal to this route, 3 into minus 660 kilojoules per mole, right? So this relationship is also referred to as the Hayes law. This relationship is also referred to as the Hayes law. We can so write like this, applying Hayes law or Hayes' law, right? So as long as the initial and final states are same, the enthalpy change or change in a thermodynamic property occurs. It's going to be the same. That law is referred to as the Hayes law. So applying Hayes law will give you this relationship. So with that, we can substitute delta H naught R. So if you substitute delta H naught R, that will be equal to this value minus this value. So this becomes plus. So it will be given as minus 1023 kilojoules per mole. Right now, that is how we are supposed to apply the Hayes law to solve the question number 1 appeared at the page number 17. Clear? Right. You can complete the note. Right. Actually, no need of writing these boxes when you write those answers in your question paper. Right. I just written the boxes to get some clear idea, to concentrate you on the points what we are discussing, right? Okay, so no need to draw these boxes, right, in writing the answers. right? Okay, so you can complete the stuff, right? So just complete this thing. Right. Let's solve the second question as well using a thermochemical cycle. That's C2H6, that thing. Using a thermochemical cycle, let's try to solve for that thing as well. Right. Right. Solving problem on 2. At page 18, no? Using a thermochemical cycle. Right? Okay. Right. So first thing to do is write in the required thermochemical reaction. So they are asking us to find out the delta R of this thing. (7O2) O2 gas to produce the 2 of CO2 gas plus 3 of H2O liquid. Right? That is what they are asking. They are asking to find out this thing. Right? Right. So some data also given. What are the data given? Data given. So they have given some data about C2H6 altitude if values are given. CO2 for the H2O liquid as well. -84, -393, -285. Right? These data are given. Right. Let's use this data to construct the thermochemical cycle and come up with the answer. First thing to do is coming up with the acceptable imaginary state. Coming up with the acceptable imaginary state. That is the first thing to do. Acceptable imaginary state. So to come up with the acceptable imaginary state, first look at the data given and see the missing pieces. See the chemical species which are not already written with your diagram. Right? Again, it's about formations. Formations involve one more substances as well as constituent elements. Reference forms of the constituent elements. Right? This is all about a system. It's all about a system. It's all about states of a system containing 2 carbons, 6 hydrogens, and 7 oxygens. Even though the 1 mole compounds are written, right? 1 mole compounds are already written in our diagram. Not all the reference forms related to the system is not written still, right? That means even though the reference form of O2 is appearing, right, these 2 are not appearing, so that we need to construct our immediate state, right, with the use of reference forms of your system, right? So the carbon's reference form is carbon solid graphite, right? You have such 2 carbons in your system, and the hydrogen is there in your system, so its reference form is H2 gas. Such 6 hydrogens are there in your system, so multiply it by 3. By looking at one state is enough, right? Don't need to look at both the states, right? Because with both states same number of atoms are appearing. This is a closed system, mass conserved, right? Plus, right, 7 oxygens are appearing. That means reference form is let's see. This is the immediate state. That is done. Now we have to relate this immediate state to the other existing states with the energy changes, with the reaction arrows and the energy changes. Right. Let's first concern these 2 guys. Converting this to this or this to this. First, identify the change. Identify the change occurred when converting this to this or this to this, right? For that, you need to identify the unchanged species. The species not changed between the 2 states. The O2, 7/2 O2 guys won't change when converting this to this or this to this. So the change here is actually converting these 2 guys to here. If you can convert these 2 guys to here, this whole state, this whole immediate state will convert to this whole state, right? So actually when concerning this, it is what? You have the reference forms of some elements and you have some compound with those elements. Reference forms of certain elements are there and you have a compound with those elements, only with those elements. That means this is all about the formation enthalpy of that compound, right? All about the formation enthalpy of that compound. So you can apply this energy change to convert this into here. What is the energy change? The formation enthalpy of this thing. So to form 1 mole of C2H6, that is what we required, we need to do this kind of energy change, minus 84 kilojoules per mole. Right? That is the energy change we need to supply to convert these 2 to here. That will convert this whole system, this whole immediate state to this whole state. Right now? Right. Then let's move towards the other one. Converting this to here. First, see the unchanged species. Basically, there is no unchanged species, right, when converting this to this. All are changed anyway, right? These are the reference forms. These are the reference forms of some elements, and here you have with 2 compounds which are with those same elements. So reference forms can be converted to these same elements, so these compounds, reference forms can be converted to these compounds by applying some formation enthalpy changes, right? So starting from the reference forms, we need to come up with here 2 moles of CO2 and 3 moles of H2O starting from the reference forms. So to produce 1 mole of CO2, you need to apply this energy change, but we now have to produce 2 moles of CO2. So twice we need to apply this one. So that is 2 into minus 393 kilojoules mole. If you are applying this energy change, right, 2 of carbons will combine with some of the O2 gases to produce, actually with 2 of O2 gases to produce 2 of CO2 gas if you apply this energy change. And we need to produce this thing as well to convert this state totally to this state. So for that we need to produce 3 moles of H2O. We need to produce 3 moles of H2O. So if you are to apply right this energy change, that will convert your reference states to 1 mole of H2O liquid. So we need 3 moles of H2O liquid, so that we need to apply this energy change thrice. So that will convert your reference states to 3 moles of H2O liquid. So by doing these 2 energy changes at once, you can completely convert this image state to this state. The state containing reference forms to this state. Right now? So our cycle is completed now. Then we need to apply the Hess law. Applying Hess law. To apply the Hess law, first you need to come up with the initial and final states. So this is the initial state where all the arrows begins, and this is the final state where all the arrows ends. Here. This is the initial state, all the arrows begins. This kind of intermediate state, right? So 2 routes are available to go from initial to final. This is one route and this is the other route. Both of those routes should carry the same value for the enthalpy change, that is Hess law. So this plus this, that is the total enthalpy change happened going through this route, should be equal to total enthalpy change happened when going through this route. This plus this should be equal to this, right? So minus 84 kilojoules per mole plus this delta H naught R is equal to this route value, that is 2 into minus 393 plus 3 into minus 285, right? So you can simplify these numbers and come up with the delta H naught R. So I'll write it straightly. It should be the same value you had got from the application of equation. That was 1557. No? Should be the same value as the answer got from the application of equation, right? හරිද? ළම අතම equation එක කියලා කියන්නේත් මේකම තමයි. අතන මේ මොකද්ද? පොඩ්ඩක් මේක හිතලා බලන්න. What are these values? Actually this is all about the delta H naught F. This is all about the delta H naught summation of delta H naught F values of products නේද? මේ products පැත්තනේ වැඩි. reaction එකේ. මේ reaction is reactants පැත්තනේ. Right? So this is the summation of delta F values of products ne? This is the summation of delta H values of reactants ne? හරිද? ඒ කියන්නේ මේ පැත්තෙන් කොහොමද? මේ reactants. මෙතෙන් products නේ. So R මොකද වෙන්නේ? Delta R is equal to delta F of products when this comes to there minus F of reactants. හරිද? අර equation එක එනවා. හරි? මෙතනදී delta F of reactants within delta F of products. එතකොට අත්තම delta R subject කරලා පස්සේ it is going to be delta F of products minus the reactants. මේක හැපතට යනවා. අර equation එක හැදෙන්නේ ඕක තමයි. That's how the equation is came, right? කතාව තමයි දින්නේ. පැහැදිලිද? හරි. ඉතින් thermodynamic cycle එක තමයි අතන fundamental එක. That is the fundamental. From that fundamental that equation came. පැහැදිලිද? හරි. ටික වැඩි එහෙම තමයි. අවශ්‍ය දේවල් කම්ප්ලීට් කරගන්න ළමයි. හරි. thermodynamic cycle එක ගන්නකො මේ product reactants කතා ලියන්න ඕනේ. Just write the things what I have written in blue color. That's all. Right? Okay. Complete the stuff. Right නේ? හරි. අපි බලමු ඊළඟ question එකත් ඔයාගේ. Right. ඉතින් අපි ඊළඟ question එකත් බලමු. So the second question. The question number 2 appearing in the page number 19. අපි එකත් පොඩ්ඩක් බලමුද. Just solve for that. solve කරන්න. Next one. Right. Solving the problem 2. Appearing in page number 19, no? Page 90. Yeah, page 90. Using a thermodynamic cycle. Right. First of all, let's write the data given. These are data given, right? Delta H naught F values are given for few compounds. NH3, NO gas and H2O gas. Right, compound එකයි delta H naught F එකයි. NH3 gas, NO gas and H2O gas නේ. As an H2O gas. What are the values? Minus 46, minus 90. And the final stuff is minus 241. The values to the right now. Okay, let's try to solve that question with the use of a thermodynamic cycle. Right, so what is the problem they are asking? They are asking about the problem is to find out the distribution R for that reaction. The reaction of 4 of NH3 gas plus 5 of 4 to that reaction, right? So constructing thermodynamic cycle, the first thing to do is actually come up with the thermochemical reaction related to what they are asking. So what they are asking is to find out the distribution R of this thing plus 5 of 4 giving you 4 of NO gas plus 6 of H2O gas. Right? What task is to come up with delta H naught F value of this thing. Right. Okay. First thing to do is constructing a thermochemical cycle. Constructing a thermochemical cycle, first thing to do is coming up with the immediate state. So look at the data. Right? This data involves the formations. That means the 1 mole compounds and the corresponding constituent reference states of the constituent elements should be there. But only the reference state of oxygen is already written, not the reference states of nitrogen and the hydrogen in this system. So let's construct the immediate state with the use of reference states of those elemental compounds. So that is nitrogen appears as N2 gas, So we have 4 nitrogens in our system, so that 2 of N2 gas plus hydrogen, the reference state is H2 gas. We have 12 hydrogens in our system, so 6 of H2 should appear to conserve the mass. And the oxygen's reference state is O2 gas. We have 10 oxygens, so 5 of O2, 10 oxygens in system. Right? Okay. So the reference forms have been written. Now our task is to connect this state to the other states with the use of energy changes. First, see the change occurred converting this into here. First this one, afterwards the other one. When converting this into this thing, 5 of O2 won't change, still appears as same. So to convert this state to this state, what you need to do is to convert these two guys to here, right? So actually when thinking of that thing, these are the reference states, some of the reference states, and this is the compound with those reference states. This is the compound with elements with those reference states. So we can think of relating these two things with the use of a formation enthalpy, right? Reference states are converted to a compound. Right? But the thing is, you are not supposed to form only 1 mole of the compound, but 4 moles of compound. So 1 mole of compound needs minus 46 energy change, but you have now 4 moles of compound, so you need 4 into minus 46 kilojoules mole energy change to convert completely the things to 4 moles of NH3. So that's all. With that, with the supplement of this energy change, these two guys will convert to here. So that will totally convert this whole system to here, because nothing happened with the 5 of O2, that thing also will appear here. No? So that this energy change will totally convert this image states, so this state to this, right? No? Okay, that is done. Let's come up with the other ratio, converting this into here, right? First see the change occurred. So basically all the species here has changed to here, no species with unchanged form. But what you know is, this is all about reference forms. This is all about reference forms, and you have some compounds here. So what you need to do again is converting reference forms to some compounds with elements with the same reference forms. That is all about formation enthalpies. So applying formation enthalpies, we can convert the state with reference forms to a state with some compounds with elements with those reference forms. Right? So let's do the conversion. So here, when converting, we are supposed to produce 4 moles of NO gas and 6 moles of H2O gas. 6 moles of H2O gas. Right? So to produce 1 mole of NO gas started from the reference states, you need minus 90 kind of energy change. But now we need to form 4 moles of NO gas. So you need to apply this energy change 4 times to form 4 moles of NO gas starting from the reference states. So it's 4 into the minus 90. That will convert this N2 guys as well as 2 of O2 gases to 4 moles of NO gas by doing this energy change. That is not enough to totally convert this state to this. You need to produce 6 of H2O gas as well. So that can be done by applying 6 times the formation enthalpy of H2O. The reference state can be converted to H2O by applying the formation enthalpy of H2O, but you need to form such 6 H2O molecules, 6 H2O moles, so that you need to apply that energy change 6 times. So that is going to be 6 into the formation enthalpy, this one, right, of the H2O gas, that is minus 241. By applying this whole energy change, right, enthalpy change, you can totally convert this state to this state, right now. Okay, that is done. Now we can apply the His law to come up with delta H naught F. So this is not the F now, this is just R, right? This is R. To come up with delta H R, we can apply the His law. To apply the His law, first you need to identify the initial and final states of the system. So with this system, this is going to be the initial state where all the arrows are originated, and this is the final state where all the arrows ends. So applying the His law will give you the enthalpy change occurred by this root will be equal to this root. So this plus this will be equal to this, right? That is 4 into minus 46 kilojoules mole. I'll write the value at once. That is going to be, this value is 194, no? Minus 194, right? Sorry, 184, so 184, minus 184. Plus this delta R is equal to this plus this. So I write 4 into minus 90 plus 6 into minus 241. Right? Okay. So that we can copy the delta R. That is going to be equal to, I'll do the simplification. So this is just minus 360, no? What about this? Let's write as 6 into 241. That is 1446. So you have to add those things as a minus value. Plus 360, no? 1806. 1806 is there, right? 1806 is there. So that is a negative value, and this is the positive value, 184. Right? 184. Right now? So this becomes as positive. It's going to be 1622. It is going to be a minus value, right? 1622, a minus value. Right now? So that is the delta H naught R, right? Okay, so that is how we are supposed to solve this one. Right? Okay, you can complete the notes, right? This is all about problem 2 appearing at page 19. Right now? So with this one, we will wind up to this lesson, right? Actually, what we have studied today is all about the delta H naught F, the formation enthalpy, right? We had done all the problems appearing in your note as well. So you have some problems to solve with your workbook. Just do those stuff, and I'll send you the answers, right, to your group, right? Then that's all for today. Goodbye then. finished it.